Hello guys, welcome to Deep Codes, and in today's video we will discuss leetcode question 802 that says find eventual safe states. So guys, first we will make one powerful observation here, and then based on that observation we will derive our approach. So yeah guys, stick till the end and watch the complete video. Now here you are given one directed graph of n nodes numbering from 0 to n minus 1, and if the graph is represented in this form, let's say for each node I we have graph of I. That means there is an edge from a node I to all the elements that are present in the graph of I. So we are given the graph in the form of 2D vector, right? So let's say this is 0 1 2 3 4 5 6. So this 0 and inside the 0 we have 1 comma 2. That means there is an edge from node 0 to node 1 as well as node 0 to node 2. Here there is an edge from node 1 to node 2 as well as 1 to 3. So this is how the graph is given in this question, and this is a directed graph, right? It is not bidirectional, it is a unidirectional, and the direction is stated by 0 to 1. That means the edge originates from node 0 and it terminates at node 1. So it is something like this, 0 to 1. So similarly all other edges are given in this form. Now our aim here is to find the number of safe nodes, and we need to return all the nodes that are safe. Now what is the definition of safe node? So safe node states that if every possible path from that node leads to a terminal node, then it is a safe node, right? So a terminal node means a node that has no more like outgoing paths, right? So that is a terminal node, means you cannot traverse to any other node from a given node, then that node is a terminal node. Now all these nodes, that's all the nodes whose all the paths lead to a terminal node, then that is a safe node. Okay, let's try to understand this with an example. So here we are given 7 nodes numbering from 0 to 6. So if you see this node 0, so its one edge is at node 1. So from the node 1 you can see there is one edge going to node 3, and from 3 it is going back to node 0. So you can see this node 0 don't have the terminal node. Although if you see one path of a node from node 0, it goes to 2, from 2 it goes to 5, and 5 is a terminal node. But a node is safe if all possible paths starting from that node lead to terminal node. See, from a node 0 there is one path that leads to node 1 and other path that leads to node 2. So the path that leads to node 1 is not terminal, right? It's not terminal. Why? Because you can see that if you go from node 0 to node 1 and from 1 to 3, so there is again a path from 3 to 0, right? So this is something like a cycle and it is not ending. So this is a non-terminal edge from 0 to 1. But if you move from 0 to 2, so let's say 0 to 2, then there is one edge from 2 to 5. Okay, there is, and so yeah, this will leads to some terminal. But although one path is not terminal, so we haven't taken 0 as our answer. Now similarly for 1 you can see from 1 to 3 and 3 to 0 and again 0 to 1. So this is a cycle. So 1 is also a part of a cycle. So yeah, we cannot take 1 as a safe node. Now a node 2, see guys, the node 2 has only one edge, that is from 2 to 5, one outgoing edge. And 5 is a terminal node because it doesn't have any outgoing edge. So yeah, 2 to 5 is a valid path, right? It is a terminal, and there is no other path that starts from 2. So yeah, we can count 2 as our answer. Okay, got it. Now talking about 3, we already know that 3 is a part of the cycle. So yeah, 3 is not a safe node. 4 has only one outgoing edge to 5, and we all know that 5 is a terminal node. So yeah, this node 4 is also a valid answer because it is a safe node. For node 5 and 6, they don't have any outgoing edge. So yeah, we can definitely tell them that they are the safe node. Okay, got it. So yeah, I hope you guys have some now somewhat understanding of a terminal nodes and a safe node. So terminal nodes is nothing but a node with no outgoing edge, so that is terminal node. And a safe node is a node whose all the paths leads to a terminal node, right? So in all the paths of a safe node leads to a terminal node, then yeah, that's a safe node. Okay, so similarly you can solve for the second example. You can draw a graph and you can easily solve this. Now what observation we have made here is, if a node is a part of a cycle, then it can never be a safe node, right? Got it? See, here the node 0 has two paths, one that is to node 1 and other to node 2. The path from 0 to 2 is a safe path, because this can lead to terminal. So yeah, if you choose this path, then we can say node 0 is a safe node. But there is a possibility of taking a node 0 to node 1 path, and that won't lead to terminal, right? So yeah, that's why we can say that since node 0 is a part of a cycle, see, there is a cycle from node 0 to node 1, node 1 to node 3, and again 3 to 0, right? So a node that is a part of a cycle can never lead to a terminal node, right? Because we want every possible path for a given node to make it a safe node. But for a node that is a part of a cycle, it will consist one such path that will never lead to terminal, right? It will consist one such path, right? So every possible path condition won't satisfy, this won't satisfy. So for any given node, if it is a part of a cycle, then we can surely tell that it can never be a terminal node. So what we can do is we can remove the nodes that are not safe, and the remaining nodes would be safe node, right? It is one and the same. Either we would find out which are the safe nodes, or we would discard the nodes that are not safe, right? It is one and the same thing. So guys, using this observation that the nodes that are part of a cycle are not safe, then what we would do is we would try to find if the cycle is present, and yeah, if the cycle is present, then what all nodes are a part of the cycle, right? We would try to find that, and all the nodes that are part of a cycle will never lead to terminal nodes, so they are not safe, right? With a simple observation, we can easily come up with an approach, right? So if you have made this observation, then it would be easy for you to get this, right? And I don't think that this is a tricky observation. If you have solved 2 or 3 test cases, then you can easily come up with this observation that if a node is a part of a cycle, then it would never be a safe node, right? So as we have seen here, that there is a edge from 0 to 1, 1 to 3, and 3 to 0 that leads to a circular path. And yeah, the 3 nodes 0, 1 and 3 won't be a safe nodes because they are a part of a cycle. So this is our approach 1, where we would try to detect a cycle using DFS in a directed graph. We would try to detect the cycle, and if a cycle is present, then we would find what all nodes are a part of that cycle. Okay, how we would do that? So this is a simple algorithm to find cycle in directed graph. So if you have somewhat understanding that how we find a cycle in a directed graph, then this is very much easy for you to understand. This is the same algorithm. So what we do here is we traverse the graph using DFS. Then we make two Boolean array, that is visited and DFS visited. Now if the graph is undirected, then one simple Boolean array, that is visited, is enough. But since this is a directed graph, we have to take two different visited array. One is visited and second is DFS visited. So this visited is a normal or general visited array that we take, but this DFS visited states that whether the node is visited in the current DFS call or not, right? So this is to track the back edge. Okay, see, now on visiting a node, we mark both the node visited as well as DFS visited as true, right? On traveling back after visiting the node, we again mark DFS visited equals to false, right? Because the current DFS call ended. So this is the for the complete DFS, and DFS visited is the for current DFS call, right? So yeah, the thing is that if a condition occur where we have visited the node as well as the node was visited in the current DFS call, then that means there is a loop or a back edge, right? And in that case, we can tell that yeah, this is a cycle. So in a directed graph, if a condition occur where visited of the I equals to true and DFS visited of I also equals to true, that means the node is visited as well as it is visited in the current DFS call, and now you are trying to visit it again. That means in the current DFS call it is already visited and you again came back to the same node, then that is a cycle. So yeah, using this algorithm, we can find the cycle present in the graph, as well as we can find what all nodes are taking part in that cycle. So let's see the coding part here. So here we made two Boolean vectors visited and DFS visited, and we ran a DFS call if the node is not visited from 0 to n. Now in the DFS call, as I already told, what we did is we first mark the node, current node, is visited in both these arrays, right? Then we try to traverse all the child. So now that is the child is present in the graph of the node. So graph is a 2D vector. So this way we would traverse. Now, if the adjacent node is not visited, if the adjacent node is never visited, yeah, then what we would do? We would try to make a DFS call, and if the DFS call returns true, then we would directly return true. Okay. So this is the thing. See, let me try to explain you. So 0. Let me try to make one graph and explain you. 2 and 4. Okay, so let's say this is a graph. Now you are making a DFS call to 0. Now you mark both DFS as well as DFS visited to true. Then one of the adjacent node is 1. Okay, right? So now 1 is not visited. So make a DFS call for 1. Okay, you made DFS call for 1. Then you now the adjacent node to 1 is 3. You made DFS call to 3. Now from 3, the adjacent node to 3 is 0. And at that point, okay, now at this point you have made a DFS call for 3. Okay, now at that point this condition won't hit, right? Because 1 is visited. But this else if condition that states that the node 1 is visited as well as it is visited in the current DFS call, right? And that means there is a cycle. So if this condition occurs, right, that there is a cycle, then we simply return true, right? So here from 3 we return true, right? We return true here. So true, this answer went to this DFS call for 1. Then that answer went to DFS call for 0, that true answer. So we check, if we get true here, then we simply return true. And we won't check for this edge, then we don't check for this edge. Meaning, see, for node 0 has 2 edges, from 0 to 1 as well as 0 to 2. But we already get true in the answer. That means we already found that there is a cycle in the graph. Then we are not checking here for another edge. We are not checking for this. And we simply return true here in that case. If this would result false, then yeah, we would check for this second edge. Okay, second path from node 0. Right? Got it? So this is how this for loop will works. That if the node is not visited, then we try to visit the adjacent and we check. If we are getting a cycle from the adjacent node, then we simply return true and won't check for other adjacent nodes. Else if we also check whether the adjacent node is visited, and if it is visited in the current DFS call, then in that case return true, right? Yeah, if none of these conditions satisfied, we try to check for other paths. Okay, got it? Now this so this is the current DFS call. So the current DFS call ended, then we again make DFS of node equal to false. We again mark it as false because the node has not been visited in the current DFS call. Now guys, all the nodes whose values in the current DFS means is true, that means they are visited in the current DFS call and they never came till this point, means they never came to this point where we are again marking to false. So all those nodes whose value would be true in this array DFS visited are the nodes that are not safe because they are the part of the cycle. Okay, since see, if the cycle is not there, then only our call reaches till here. If the cycle is there, then we would return true at any of these places. But if the cycle is not there, then only our call will come to here where we are marking the node as false in the current DFS call array. Okay, so this DFS is we are marking it false. But the nodes that are part of a cycle won't reach till here, and that's why all the nodes that are whose values are true in this DFS list are the part of the cycle. Okay, so that's why here we simply check if this value is true, then we simply means if this value is not true, then we simply push that node into our answer because they are the safe node, and if their value is true, that means they are part of a cycle at some DFS call. Okay, got it? So yeah, that's how this code is working, right? So if you have this understanding of how we can find whether there is a cycle or not in directed graph, then it's easy. The only trick was to do this. Then the only understanding you need to find is for this, right? Okay. Now, guys, this is one way to solve this question, and the time complexity here is big O of n, as well as the space complexity is also big O of n, right? Now, there is one another approach to solve this question. Now, if you take a look at a terminating node, then the terminating node won't have any outgoing edge. or the out degree of that node would be 0, then only it would be terminating. There is no outgoing edge from that node, then that is a terminating node. So the nodes, so the termination means out degree is as 0, and nodes that are not a part of a cycle would somewhere leads to termination, right? All the nodes that are not part of cycle would after some steps, let's say 5 steps or 7 steps, would lead to termination. Okay, and termination means nothing but out degree equals to 0. So what we can do is we can start with the nodes with a 0 out degree. Okay, we can start with a node with a 0 out degree. Let's say that node is some node x. Okay, so this node x has a out degree 0. Now what we can do is we can decrement the out degree of a nodes, neighboring nodes to node x. So let's say there is a node y to node x and z to x. So this graph is something like this. Now you can see the out degree of this is 0 and this is 1 and 1. Out degree is 1 because there is one edge going outside. Now since this is 0, what we can do is all the paths that are coming towards the x, right? So there is one path from y to x and z to x. So we would keep on decrementing the out degree. So this is 0, then the adjacent is this, so we would decrement to by 1. We would also decrement this by 1, and we will do off until we can, like we would keep on decrementing until we find the adjacent nodes, right? So and at the end all the nodes with out degree 0 would be our answer. Bit confusing? Let's try to make a dry run. So let me first give a numbering of the out degree. Here out degree is 0, 0, here it is 1, here it is 1, here it is 1, here it is 2, and here it is also 2. Now as I told you, we would start from the nodes with out degree 0. So first is this node. Okay, then we would decrement all the nodes that are to which this node is adjacent. So there are no node for which this node is adjacent. So yeah, we would stop that call. Then we would take the second node with the out degree 0. Now that is this node. Okay. Now we would also decrement the out degree of the nodes for which this node is adjacent. So 5 is adjacent to 4. So we would change or decrement this by 1. So this would be 0 now, and this would be 0. Now afterwards we would take another node that is having out degree 0. That is node 4. Now do node 4 is adjacent to any other node? No. Then we have node 2 with out degree 0. Is node 2 adjacent to any other node? Yeah. So that is node 0. So we would again decrement it out degree by 1. Okay. Now after this, there is no nodes present with out degree 0. So we will stop. And afterwards, so now we have reached the end. And you can see that all these nodes with out degree 0 are our answer. Simple it is, right? All the nodes with out degree 0 are our answer. Okay. So what here we have did is we have done a BFS call, right? So let me try to explain you with the code. So we have initialized this out degree vector, this adjacency list. Now here as you can see that let's say if we are at node 4, instead of node 4, let's say we are at node 5 here. Now here what we are doing, we are decrementing the out degree of this as well as this, but there is edge from 4 to 5 and 2 to 5, right? So in order to find who the nodes to which 5 is adjacent, we are adding a reverse edge. We are adding the reverse edge so that we can know that node 5 is adjacent to what other nodes, so that we can easily decrement the out degree. So that we are doing here, that we are simply making a reverse edge. We have taken a new adjacency matrix, adjacency list, and we are making a reverse edge. We are simply making a reverse edge from the graph of ij to node I. Okay, we are simply making here a reverse edge, as well as we are calculating the out degree. Out degree is nothing but number of edges going outside. So that is nothing but a graph of I dot size, as this is a 2D vector. So we can directly take the size, as we can know how many edges are there from that node. And yeah, we have and we will do a BFS call on a nodes with the out degree 0. As I told you, we would start with the nodes with the out degree 0. Then for that, we also initialize one queue, and we simply push all the nodes inside the queue with the out degree 0. So if the out degree of a node I is 0, then simply push that to the queue. Now this is a simple BFS call where we remove the topmost element or the element present in the front of the queue. Then we mark it as safe because it has the out degree 0. Then we traverse all the adjacent node and decrement the out degree. and if at any point the out degree of the adjacent node becomes 0, then again push that to the queue, right? We push the new nodes to the queue if their out degree is 0, right? Got it? So yeah, and every time when we take the front element, we are marking that element as a safe, and at the end all the elements that are safe we would push in the safe nodes, right? So yeah, this is the second way, or you can say this is a reverse engineering we are doing here, right? We are taking the terminal node and marking the other nodes as a terminal by just decrementing their out degree, right? So yeah guys, this is the second approach to solve this question. Now the time complexity here is also big O of n as well as the space complexity, right? Overall it is big O of n here, right? So yeah guys, that's all for this video. If you guys have still any doubts, then do let me know in the comment section. But one thing here, the time complexity, because this is a 2D, we are traversing 2D for loop and total elements are n plus m, so my bad, time complexity would be n plus m. For all n nodes there are, let's say, m edges. So yeah, means how many edges are there that we are traversing here, so that many times would be our time complexity. Okay, you can figure it out, this thing. So yeah guys, I hope you understood that what we are trying to do in this question, and if you have still any doubts, then do let me know in the comment section. Make sure to like this video and subscribe to our channel. Thank you.